just a quick overview. All right. So as I was saying, right, knowing how to calculate the probability of something occurring, the first way that we learned was classical, right? Classical probability, or theoretical in parentheses there. So again, interchangeable words, classical, theoretical, they're the same thing. And you're just counting each event equally, right? So the probability, for example, of you selecting a card out of a deck of 52 cards, right? And that card being a 7 of diamonds, you just count how many 7 of diamonds are there, and there's just one of them. So then you say, oh, the probability of you drawing a 7 of diamonds is 1 out of a total of 52, and that's it. If it was worded differently, if it asked you instead, what's the probability of you drawing a 7, right, out of a deck of cards, you count how many 7s there are. 1, 2, 3, 4. There's 4 in total. That 1/4 was for something else, Michael. Oh, that 1/4 was for the event of you selecting a diamond. So I'll show you that one in a second. But right here, right, if you're just asked to draw a 7 and they don't specify the suit, they just say, what's the probability of you getting a 7, right? You'd measure that out, and that comes out as 4 out of 52, right? Or in other words, 1 out of 13 if you reduce it. Now, I had a 1/4 written there earlier. That's because for this part right here, what if you were asked to find the probability of selecting a diamond, right? And you count how many diamonds there are. Well, when you count how many diamonds there are, that's this whole entire column right here. And they tell us that there's 13 diamonds. So that lists out that it's 13 total possibilities, right? You're counting it out. There's 13 of them out of 52, right? You're not doing this 52 times and seeing that, oh, 13 times I picked one card. 52 times I picked a card, 13 of them came out as diamonds. I'm not observing that. I'm just counting the possibilities, right? Yeah, and if you reduce the 13 over 52, it comes out as 1/4. But the reason why I had 1/4 written down earlier was that if you look at the number of suits there are 1, 2, 3, 4 suits. And out of the 4 suits, if you select a diamond, it's technically one of the suits out of the 4 possible suits, which happens to be the same answer that we get if we simplify the 13 out of the 52. And I just wanted to show you that that's an interesting little connection there, right? It's the same concept. And that's the beauty of classical probability, is that you can make those connections, right? If you're just looking at a specific suit, then it's just going to be 1 out of how many suits there are, right? But you could also just add up how many cards you have of that suit, and it comes out, the math comes out the same. The math comes out the same, at least in a deck of cards, just because there's the same number of hearts, there's the same number of diamonds, there's the same number of spades, and there's the same number of clubs, right? So that's a little tricky though. Like, I'll put this back up in a second, but that's a little tricky though. If you said, for example, you had a bag of marbles. You guys remember those problems when you first learned probability? You always learn it with a bag of marbles. Have you ever learned this before? And in that bag of marbles, right, they always have like a set number of different colors. So they'll have like 3 blues, 2 reds, and like, I don't know. Why am I drawing a blank on picking random numbers today? 5 greens, right? So technically, give me a second here. I'm gonna change the thickness of these pens because they look a little skinny. So if I have, category of blue, right, and then a category of red, and then a category of green, if they're not equal all the way through, then that trick doesn't work, right? For example, here, how many marbles do I have in total here? 3 + 2 is 5 + 5. I have a total of 10 marbles in this bag, for example. So if I was looking for the probability of you drawing a blue marble, it's technically 3 out of 10, right? That's not technically, that's officially what it is. But if there were equal number of marbles all the way across, then you can see that, oh, there are 3 different colors, right? And some people would say, oh, the probability of you drawing a blue, if there's only 3 colors, some people want to say that it's 1 out of 3. But it's not the case if there are a different number of marbles in there, right? If they're not equal, then they are not going to equal each other, right? The number of colors and the number of marbles, if they do not equal, then it won't equal out. Whereas on a deck of playing cards, the number of hearts, the number of diamonds, the number of spades, and the number of clubs, they all equal all the way across the board. So you can make that connection between the two with the number of suits you have and the which suit you care about. Anyways, that's not really that important. It's just I just like talking about probabilities. Like I said, it's really fun once you get into it, and actually once you start getting the hang of it. I'm telling you. I think I talked about this briefly. If you guys ever decide to go into like, to just for fun, when you hit 21 and you decide to go to Vegas and you decide to play some blackjack or play some dice games or something like that, it's really fun to look at the probability behind it and calculate odds of you winning and how much you should get paid if you do win. And it's just that I'll just give you this hint right now. Once you actually start calculating, you're going to realize how much of a scam Vegas actually is and how much it is like it feels like you're winning, but you're actually not getting paid the fair amount. And yeah, the saying the house always wins isn't being said just because, oh man, I'm always losing. It's mathematically proven that the house always wins. That's how they stay in business. So they sell it as not the fact that you can get rich, but they sell it as a experience for having fun. It's like, yeah, don't think of it as a chance to get rich. Think of it as a thrill, right? That's all it is. That's the way they sell it. They sell it as a thrill experiment. Thrill experience, right? But yeah, mathematically though, once you start learning this stuff, it's really fun to look at. But then at the same time, you're gonna realize you shouldn't gamble. It's not the way to get rich. Is it hard to win a lot of money? Yeah, no, it depends. You can. How do I explain this? More than likely, you'll probably stay around a specific area. You remember this bell-shaped curve that you guys had to learn? Right? This bell-shaped curve. The idea is if you go on the positive side, this is you winning money. And if you go on the negative side, this is you losing money. And the middle is you breaking even. Right? If you look at this bell-shaped curve, most people stay within one standard deviation, meaning if they win money, they win about one standard deviation above. And if they lose money, they usually lose about one standard deviation below. And how much is that when you're talking about money? It all depends on how much you're about to bet, right? So there are a few people who get really rich. That's 2 standard deviations, but that's considered far. And there are people who get really broke, and that's 2 standard deviations below. So the chance of you getting really rich, like hella rich, right, is hella far from the average. Same thing with you losing hell of a lot of money. That's the same thing right there. So that's starting to combine like probability with statistics and number placements and all that stuff. But again, once you learn the basics and you want to apply these things, it's really fun to do. Like probability was the first thing I started applying it to, but then you start seeing other things that you can apply statistics to and you can apply probability to. And it's just really fun to do. But you got to get through the calculating part. And I know a lot of people are just like, I don't want to calculate this stuff, but it's fun, honestly. And then who was saying you got rich by gambling on GTA? I forgot they added that to the GTA Online feature. I have GTA Online on both my PS. This sounds old. On both my PS3 when it first came out, and then I have it on my PC as well. And then I went on there once, and then I've never gone back. I know that there's been a lot of things added, but I just never gone back on there. I should check it out. But I feel like you have to earn a lot of money online to get stuff, right? Or some, I don't know, random stuff. You get a free car by doing a spin in the casino. Yeah. A fun thing for you to do is calculate the probability of you landing on the slot for the free car. You know that? If you're calculating the probability classically, you count how many spots that the wheel can land on, and usually it's over 200. And how many spots say that you can win a free car, and most times it's just one. So when you spin it, the chances of you winning would be one spot out of the total of 200 something spots that are on that wheel. But that's how you could do it classically. What we're going to talk about today is empirical probability. Empirical probability. If you guys want to write that down. GTA in the casino. Yeah. I'm assuming the same thing, but it's a free spin, so you have nothing to lose. That's how they get you in the real casinos too. Hey, it's a free whatever. They get you in the casino, and then you're like, well, I might as well gamble while I'm here. You know, I kind of want to open up. I want to open up GTA Online now on my computer. Anyways, so filling out your notes. Empirical probability is very similar to classical probability, but in a sense that you don't actually count computationally. You count based off of what you observe. I thought you say I want to open up a casino. I mean, in theory, I think everybody wants to open up a casino. The only problem with opening up a casino is you need to have like the hundreds of millions of dollars before you could do it. But then once you have it open, casinos make like literally make a lot of money just by existing. Like that's all it is. Even during the pandemic, you know, casinos like decided to reopen early during the pandemic, and people, I was like, I haven't gone back, even though I love gambling, but I don't want to, you know, people are disgusting and they're sitting next to each other, and I don't think there's any way that the casinos could do it. But that's how bad like gambling is for some people, that they're so addicted that they'll go out during a pandemic and stand next to other people. And yeah, yeah. Not gonna lie, I have an itch. I haven't gone like since over a year. I used to go quite a bit. Do what makes you happy. Yeah, at the same time though, I don't want to, you know, die from it. I feel like I'm old enough that COVID would be a problem for me. I'm not like old enough where it would kill me, but I'm old enough I feel like it would actually cause me to have breathing issues. So yeah, you know, choices. Do you want to be happy playing or do you want to still be breathing? It's okay though. Vaccine's coming out soon, guys. Vaccine is coming out soon. England just vaccinated their first 60-year-old lady. I think it was like last night or in the morning over in England. So that's exciting news, right? We're going to be pretty soon getting that over here in the States as well. I can't wait. Doctors and living facilities are going to be first. And then essential workers, I think, or something like that. And then I think teachers are going to be like somewhere in the second wave of it. Yeah, the US one is getting approved soon. They are working through it to see if it does get approved. But yeah, looking at the timeline, if we look to see who gets it first, which is probably going to be doctors and nurses, and then like all the people in the old folks homes. It's not the actual term, but those people will be getting it first in the first phase, and that should be done hopefully by like mid to late February. Even though they start doing it by the end of this month, it should take about 2 to 3 months to get all those people. We're talking about like millions and millions, like probably 20 million, tens of millions of people. And then they'll go to the next wave. And I think the teachers wave, I'm thinking it's going to happen somewhere around April. I'm hoping it'll happen sometime around April, meaning students should be next after, and then you guys should be able to get vaccinated and then come into the classroom, hopefully by like late April, early May, which then gives us just 1 month before you guys graduate, so I can actually see you guys in the classroom and actually see your faces and hear your voices. I know that some of you guys could turn on your cameras and I can see you on the camera and then see you guys and hear you guys through the mic, but this is not the same. When I go back to school before school ends, hopefully, Michael, I'm hoping that's the case. So you know what, you'll get that end of the year senior experience in school. I think that's actually the best experience, because then you don't have to worry about, all of your procrastination and whatnot. Because at that point, you're at the finish line, you've passed your classes, you're ready to graduate, and then you get to enjoy the fruits of enjoy just being around others. So hopefully. Trying to get us back in time for the AP exams. I mean, trust me, Calvin, you'd rather take the AP exams in person than do it how they did it last school year. All right, so let's take a look at this. Empirical probability based on observations obtained from probability experiments. So you observe what you do and then you write it down, right? So for example, and you don't have to write this down just yet, but classically, classical probability, when you flip a coin, the probability of you getting heads is 1 out of 2, If you're doing it empirically, you need to set how many times you're going to flip the coin and then record how many times it lands heads based off of that. So for classical, right? For classical probability, right, the probability of you flipping a coin and getting heads would just be simply 1 out of 2, because there's only one head on that coin out of 2 sides. Now, if you do this empirically is a little bit different. You need to set up a rule to say, how many times am I going to flip this coin? And let's say I'm going to flip it 10 times. Now, classically speaking, the answer on the top here, the number up top, should be 5 if I was talking about classical, right? But empirical doesn't go based off of that. Empirical goes based off of what actually lands. It's what actually you observe out of 10 coin flips. So what I'm going to do right now is I'm going to flip a coin 10 times, not physically, because that's just going to be ridiculously boring if you watch me flip a coin 10 times. But I'm going to ask Google to flip a coin, right? Oh, God, can I have it flip it 10 times? No, I cannot. Flip a coin 10 times. Let's type that in there. Flip a coin 10 times. Just a coin flip? Will you do it 10 times for me? No, you'll do it 1 at a time. How about you? Random.org. Will you flip a coin 10 times? I should have researched this before I started this up. Is there something came up? Am I able to leave right now? Because yeah, Christina, go ahead. This is recorded, so just watch this later on when I put it on YouTube, and then let me know when you finish the notes, okay? Let me know when you finish the notes. Okay. Flip 10 virtual coins. You can pick what type of coin you flip. Let's go with the 25-cent piece from Georgia. Ridiculous. Okay. Are you flipping? Oh, it actually has a picture of the coin. That's not bad. Okay, so empirical probability, right? We would go in here and we'd count how many coins landed heads. And that's the probability of you getting heads for flipping a coin. I know it sounds weird, but that's all you do. So in here, if you look, 1, 2, 3, 4. So the probability from the empirical stance, right, from us actually physically flipping, well, virtually flipping a coin, comes out to be 4 out of 10. So that's the difference between the two. You can calculate probability classically just by counting it, right? Heads is 1 out of the 2 possibilities, or you can do it empirically. And empirically is based off of how many coin flips you do or how many of that experiment you do, and divide that into how many you get of what you care about. In this case was just, I just made this up, it was just heads. And looking at that coin flip, empirically speaking, oh, I got 4 coins that showed up heads, right? So that's what I will record. So you'll say they don't equal to each other, and that's okay. That's okay. Probability will follow its own kind of like, there's observational probability, right? That's what this empirical stuff is just observing it. And then there's classical probability, which is what it should have been mathematically. And I'll show you there is a connection between the two, even if the numbers don't equal. All right, what am I trying to say with all this? Well, let's take a look here. A company is conducting a telephone survey of randomly selected individuals to get their overall impressions of the past decade. This book is old because the past decade was the 2010s, not the 2000s. So far, 1,504 people have been surveyed. What is the probability that the next person surveyed has a positive overall impression of the 2000s? What the heck does all that mean? Well, we're looking to see who would answer that they had a positive experience. So here are my responses. It's kind of small. Let's make that a little bit bigger. So here are my responses down here, and I see the number of people who would respond that they had a positive experience, right? So I'm looking for the probability that they had a positive experience. Well, how many people responded that they would have a positive experience? I had a total of 406 people. How many people were asked in total, though? Can you guys look at that chart and decide what is the total number of people who were asked to respond to the survey? How many people were asked in total? You guys see it? 1,504. That's right. That's right. Down here is the number of people who totally responded. Yeah, that grammatically is correct, right? All right, 1,504. And that's it. That's the probability of this observational this is the empirical probability right here, right? You just see it based off of what you record from people responding. So it looks like a lot more people were negative than there were positive, and there was the people who neither, and then there was 30 people who said, I don't know. So you can see that the probability, the percentage would be kind of low, and you just plug this into your calculator if you want to get a actual percentage out of this, right? So if I said how many people are positive, we can take a look here and see, 406, right, divided by 1504 has a probability of about 26.2699, right? So 0.2699, or roughly 26.99%. So about 26% of the people say that they would have a positive experience, right? So the probability that the next person says the same thing would be about 26%. We don't know if it's exactly, but we do know that that's it. And that would be your answer. That would be your answer. You guys try this one for the next one? Do these next two real quick. Actually, just do this next one real quick. Just do this, you try. This one right here. Using this table right here, a company is conditioned. Man, my reading skills are a little off today. A company is conducting an online survey of randomly selected individuals to determine if traffic congestion is a problem in their community. So far, 320 people have responded to the survey. The frequency distribution shows the results. What is the probability that the next person that responds to the survey that the traffic congestion, says that the traffic congestion is a serious problem in their community? So guys, can you guys go ahead and do that real quick? They're asking us to find the probability that it is a serious problem. Do that real quick. What is, the word problem is written weird. Yeah, what is the probability for this one? So you set up the fraction first and then give me the decimal whenever you are. Actually, don't type it out just yet. Give everybody a chance. You guys go ahead and do that real quick. Calculate that real quick and see what you guys get. Boop, 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 boop. You don't have to, Michael. You could just keep it as a decimal. I actually prefer percentages written as decimals because I don't know. It's just, I don't know why I prefer that, but I do prefer it as a decimal. So it's up to you, though. If you want to write the percentage, you can. But actually, a lot of people who do statistics, they like leaving their percentages as decimals. It isn't until they have to talk to people or write a report that they write it as a percentage. I think it's because it's easier to do the math when it's a decimal still, because you know you can multiply it by stuff. If you haven't got started so far, you should at least know how many people you should be dividing this out of, right? The total number of people that have been surveyed, they even tell you so far 320 is the total. That's the total number that goes into on the bottom. Right? So if you don't know how to start it so far, that's where you should at least have. You should at least know that the probability of this is going to be out of 320. 320. Now, if you guys already have the answer, you guys want to type it out for me in the chat. What did you get for your decimal, or what did you get for your percentage? Or yeah, type if you have it for me. Could you type that into the chat for me real quick? And no Pear Deck today. It's just going to be easy stuff. If you guys could type that out for me. Anyone want to share what they got for their answer? I don't actually know the answer, by the way. Giselle's sharing it out. She got 30.3843, and Calvin's sharing the same decimal along with that, and so is Lizzie. So I'm assuming that you guys did it right if 3 of you guys were able to get the same exact number, right? Same exact number. So that looks good. That looks good. Let's go ahead and double check if you guys got that. Thank you guys for typing that out. I appreciate it. Okay. So hopefully you guys are noticing, right, that we're focusing on serious problem, which is this guy right here, which has the number of 123. Empirically speaking, that's the number that that we're going to record for people who have a serious, or who think it's going to be a serious problem, traffic congestion, right? So we write that down. It's going to be 123 out of 320. And yeah, that's pretty much it. That's your answer. 123 out of 320. If you want to go ahead and give me the decimal, you just plug it into your calculator. 123 over 320. Boom. 0.3843. You guys got to work on your rounding. 0.3843. What's the number that's after that 3, guys? What's the number that's after that 3? Be careful. The number after that 3 is a 7, right? The number that's after, did I type it in wrong? Yeah, it's a 7, meaning that should be rounded to 3844. Now, am I going to mark you wrong if you put down 3843? Am I going to be like, no, that's completely off. You're off by so much. I'll still give you the credit. I just want to make sure you guys understand the best practice for this, right? That's your answer. If you put it in with a 3 at the end, I still give you the point. But just be careful. Just be careful. I don't think I will do something like that on your test where I put down 0.3843 and then the other answer choice is 0.3844. Instead, it'll just be a free response question, and I'll just give you the credit. But anyways, yeah, that's pretty much it, right? It's not too bad. It's not too bad. It's literally just recording what you see out of how many you've tested or how many you've questioned in total, right? So if I flip a coin 20 times and I was doing the probability of getting heads after 20 flips, it wouldn't be out of 10 anymore, it'd be out of 20, right? And then you simplify it afterwards and get that decimal out there and see what you get. Let's take a look here. An insurance company determines that every 100 claims, 4 are fraudulent. What is the probability that the next claim the company processes will be fraudulent? So what's the probability that they're going to have a fraudulent claim on the next one? Well, how many claims have they done in total? We simply just write that out. They've done 100 claims. How many of those 100 claims were fraudulent? Only 4 of them. And that's it. That's all you have to do to set this up. Okay, that's all you have to do to set this up. Plug it into your calculator, 4 out of 100, and you end up with 0.4. And that's it. How you guys doing? You guys doing all right? Does this probability stuff seem okay? It seems deceivingly easy, doesn't it? I kind of get it. Yeah, that's good. Yeah, it's that's what I'm trying to tell you guys. Probability is not that hard. It's just the fact that sometimes you have to count ridiculously large amounts of things, and it gets kind of annoying to count that amount. But the math itself isn't hard. In fact, right, you just have to know which number divides into what. And you just got to make sure which one is the, well, which one is the number that goes on top, which one goes on the bottom. Wait, oops. Did I put down 0.4 when it's clearly 0.04? There we go. I was just checking to see if you were paying attention, and you were. Good job. See, the problem was I don't have my glasses, and it's that 4 looks like it was a point, 0.4. That's all it was. Good catch, Calvin. I appreciate it. It was 0.04, not 0.4. Yeah. Yeah. That did not seem right. What'd you get as a snack, Calvin? Not math related, but I want to know. What are you snacking on? Red bean bun? Ooh. Yeah. Asian snacks. Asian snacks are the best, guys, if you ever had it. Actually, I think all snacks. Mexican candy is delicious. Oh, I'm getting myself hungry. All right. Let's take a look here. There's no competition. I don't know, Calvin. There's some things. I love Asian snacks, but there's some other snacks in, like, I know, like in Mexico, there's some snacks that I enjoy there. Are there any American snacks that I like? I mean, you grow up eating Doritos. Doritos are delicious too. Oh, Flamin' Hot. I'm sorry. You guys probably all eat Flamin' Hot Cheetos, or do people no longer eat Flamin' Hot Cheetos? Flamin' Hot Cheetos with lemon, or was it limon? Lemon? Demaya, I'm here. At least you're here. All right. We're just doing our notes right now, Demaya. So open it up. Try to catch up on it. You don't eat hot Cheetos? No? People still eat chips. I thought it was for them. So, yeah, you know what I've noticed over the past 8 years that I've been teaching is that students have gotten slowly, but more so, have gotten a little bit healthier compared to what it was in the past. I remember, I don't know if you guys had this in your middle schools. Just go get some food and bring it back, Lewis. Just get some food and bring it back. But do you guys remember the Kool-Aid gummy worms? I don't know if that was still a thing for you guys when you guys were in middle school. Did you know anyone who had, or even in high school, do you know anyone here at Lawndale that was selling Kool-Aid gummy worms? Those were disgusting. I love eating junk food. That was the most disgusting thing I've ever seen a kid eat in my life. They would always sell them. No, think about it. Think about what it's made of, right? Like gummy worms are pretty good. And then they had, Kool-Aid is not supposed to be concentrated like that. But the way I always see kids eat it was the most, diabetes in a bag. It was the most disgusting thing I ever saw. It's because you always like rip a hole in the bag and you don't want to get it everywhere. So they would like suck the gummy worm out of the hole. And it was just disturbing to watch people eat that. But you know, who am I to judge? Ugh. All right. Straight up sugar and food coloring. It's fine dining. I can't talk. I ate all kinds of junk food. I don't know if you guys ever had Flamin' Hot Cheetos with nacho cheese and jalapenos. Those were delicious. Ew. Still ate it though. I gave up chips and soda for my sport. Now I just don't like them anymore. Yeah. You know what was the biggest thing? Was I think drinking water is the biggest change that I've made in my life. Like, you ever just drink water and just realize like water is the most hydrating thing ever? Like, I used to not drink water ever. I would like, to be healthy, I thought I could just drink Gatorade, but that's so much sugar in there as well. And then you just start drinking water and it just tastes so much better. I don't know how to explain it. Like cold water, not room temperature water. Yeah, especially if you play a sport, Lizzie. Like, I don't know what sport you play, but yeah, as soon as you are practicing and then you have like that first sip of cold water, it just feels so good. Like, it just feels like your body is like being brought back to life. I think that's the best way I can say it. You can taste the difference between waters, though. Yeah, I agree, Calvin. I agree. I know some people say that that it's all the same, but yeah, I agree. You can definitely taste the difference between different brands of water. I don't know if I'd drink Fiji water though, or at least pay for Fiji water. I don't know about Fiji water. That one's like ridiculously priced. I think the highest priced water I'd drink is Smart Water. Smart Water is probably the only one I drink. Arrowhead is the best water. I don't know about Arrowhead either. Arrowhead's nice and cheap. I don't know if it's the best water. I don't see how people can drink room temperature water. I agree with you on that one, Demaya. Room temperature water is just leaves like a weird taste in your mouth. Arrowhead water is a no for me. Room temp is fine. Yeah. Aquafina is the best. You know, I don't think I've ever had Aquafina. Anyways, let's focus back over here. This whole recording is just going to be us talking about the most random things aside from statistics. All right, let's take a look here, guys. Did you guys already copy this down? This is the next one that connects your empirical probability with your theoretical probability. All right, this is the part that I think is neat. If you look at empirical probability, right? Empirical probability is the thing where you actually do the actual experiment and you record what happens, right? So suppose you want to determine the probability of tossing a head with a fair coin. If you toss a coin 10 times and you get 3 heads, right? Empirical probability says that you get a probability of 3 out of 10, right? Because you flipped it 10 times and it came out 3 heads, 7 tails, and you stopped there. Because you tossed the coin only a few times, your empirical probability is not representative of the actual probability, which is supposed to be 50-50, right? Supposed to be 50-50. So technically, if you flip it 10 times, theoretically speaking, it should have came out 5 heads, 5 tails. But that's not always going to be the case in the real world, right? That's not always going to be the case. That's because the coin doesn't actually know that it's landed heads 4 times already. And it's going to be like, oh, you're flipping me 10 times. I better come up heads on that 5th time, or else it doesn't work. The coin is still a chance of 50-50. But if you do it literally 1,000 times, it gets really, really close to 1/2. It gets really, really close to it. And I wanted to spend a little bit of time to show you that right now. Do I have the program? Actually, we could just use this site, can't we? Can we go back? How many coins can I flip on here? Oh, beautiful. I can flip like hundreds of coins. So check this out. Check this out. If I flip a coin, right? If I flip a coin 10 times, right? And I got, let's say, 4 out of 10, and I calculated that one, right? 4 out of 10, right? We got 4 heads out of 10 tries. That probability comes out to about 0.4, but we know that the probability should have been, theoretically speaking, 1 out of 2, it should have been 0.5. So it's not exact, but it's a little close. Now, if you flip the coin more times and you record what comes up heads and what comes up tails, what this theory is saying is that it should get really, really close to 0.5. It should get really, really close to 1 out of 2. And if you don't believe me, you can actually try this out. If you go to, I guess this is random.org, and we flip a coin, we flip it 10 times. Let's try flipping it 50 times and see what we get. Let's try flipping it 50 times and see what we get. So you flip 50. You know, this sucks though. It doesn't actually tell me the number. I have to actually sit here and count. So my eyes are bad, so make sure I count this correctly. How many heads is there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. We got 18 heads. I hope I counted that right. Out of 50 total tosses, right? That comes out about 0.36. Now you can go ahead and go further. Or not flip it again. What am I doing? I want the action. Can I just, is there a way to just get the numbers so I don't have to have this coin and count it out? No. Oh, is this site going to do it instead? Where, no, that's something else. No, that's not going to, darn it. All right, anyways, let's find another site that actually that does this. So I don't have to count out how many heads are there, because that's going to be kind of annoying. Let me go back to Google and see if I can get another site that will flip a coin for me. Let's go with 100 times. I don't like that random one. Is there any other sites that does this for you? I feel like there should be one that will have it. So dang it, I wish I had my programs installed on this computer, but I don't. I actually had a software that would do it for you and count it, but I don't have that anymore. Now I'm trying to find a site that does it. I thought there would be one that does it nicely, but I don't have it. What are these guys? No, we're just gonna have to put that on hold, I guess. Oh wait, does this work? Number of tosses, 100. Awesome. Ah. There we go. Ha. Okay, this site works a little bit better. So can you guys see that okay? Right, this one actually even shows the probability right here. So the probability of you getting heads after 100 tosses, it comes out to about 0.54, which isn't that far from calculating it if you were calculating it theoretically. Theoretically speaking, it's just 1 out of 2, which is 0.5. But when I toss the coin 100 times and I got 54 heads, it's getting closer and closer to it, right? And if you flip it 1,000 times, does this work the same way? You flip it 1,000 times, look, they record, this is perfect. This is what I need. I should bookmark this page. So they got 564 heads, 536 tails, right? It's not exactly matching, but look at the probability. The probability is getting closer and closer to 0.5. You see that? It's closer and closer to 0.5, which is the actual one. Can this thing flip it 10,000 times? How many numbers can I go up on this one? Oh, I can only do 1,000 times. Oh, well. Yeah, that's the idea. If I found a program that could do it 10,000 times, right? Oh, you can keep going per thousand. Hey, you guys see this? It just keeps piling on more and more. Oh, I could just keep going by the thousands. Oh, I hit the clear result button. Knock me, what are you doing? All right, so first 1,000, right? You can see that there's that right there, and just keep tossing them. There'll be 1,000. This is for 2,000 flips, 3,000 flips, 4,000 flips. What are you noticing about the percentage there for the heads? It's getting closer and closer to 0.5. I hope you can see that. It's at 0.4948. Now it's going to go to 0.496. And there's at 6,000 flips, and we go up to 7,000. It's 0.4967, right? It just keeps going. No, see, that's exactly it, Michael. I didn't make a mistake. I was doing it so the numbers would be a nice round 1,000 number instead of 1,100. That's what I was doing, Michael. It was planned all along. It was planned all along. Look at this. Look at this. After 9,000 flips, it's getting so close to 0.5, right? And if you get to 10,000 flips, right, it's practically there. It's a little bit over, but it's going to level out around 0.5. And why does this happen? This happens because of this theory right here. It's the law of large numbers, right? The law of large numbers. Meaning, if you do something enough times, it should eventually approach what the theoretical probability is. Same thing can be done when you roll a die. If you have a 6-sided die, the probability of you getting a 3, right? The probability of you getting a 3 is 1 out of 6, right? Which means it comes out to about 0.16 repeating, right? Which means that if you were to do this 1,000 times, right? Or if you were to do this 1,000 times, right? You should get about 166 of those 1,000 dice rolls. 166 of them should come up with 3. And it's not always going to be the case, but if it doesn't, then that means if you did 10,000 dice rolls, when you increase it to 10,000, it should get closer and closer to that number, right? That's all it's saying, is that it should get closer and closer as I do this more and more. And that's all the law of large numbers is. It's just a theory that says if you do something a large amount of time, it should get closer and closer to what the theoretical probability is. And you see it when you flip a coin, you see it when you roll a die, and yeah, there's other things that you can calculate the probability of and see that it is the case. But we don't actually want to do something like 10,000 times, so we end up doing like a simulator of it. You guys remember that? Simulation? It's one of the ways we do our statistics. Simulation, observation, right? Simulation is one of them that makes it easier to do. But anyways, that's that right there in the nutshell, guys. The law of large numbers is basically stating that if you do something a large number of times, you should get your theoretical or your empirical probability to get closer and closer to your theoretical probability. However, if you toss a coin several thousand times, the law of large numbers tells you that the empirical probability will be very close to theoretical or actual probability. And I think that's kind of neat. I should find something for us to practice that with. It's just kind of cool to see, right? It's just kind of cool to see. All right. This is the last type of probability, and this is probably like the worst type of probability. And we call this subjective probability. This is the last one we're going to be talking about today. So in subjective probability, right? Subjective probability, intuition, educated guess, or estimate. So an example of this could be a doctor, right? The doctor may feel a patient has a 90% chance of a full recovery. But this doctor is doing this based off of his intuition or his educated guess because he's never had a patient that's exactly the same as the patient he has right now, right? So it's impossible to say based off of old empirical data. And you can't do this classically because there's no like theoretical probability of like, you know what? I've had other Joes before, and on paper, they had a 90% chance of succeeding. So you are a Joe as well, and you're going to have a 90%. You know, you see how ridiculous that sounds? So they don't have a way of measuring that for like, at least for a doctor. So they'll make an educated guess to see how well they will succeed with recovery. And when they make that guess with that probability, that's called subjective probability. And it's not the best one, you know, subjective probability is not the best way, but sometimes you don't have a choice. You have to go with, you know, their educated guess or their estimate. Another example would be a business analyst may predict that the chance of the employees of a certain company going on strike is 0.25, or in other words, 25%. Again, they don't know if those people will go on strike or not, but they have an idea based off of what they're observing. But again, subjective probability, not the best probability, but it is needed sometimes. Sometimes you just can't tell. Like, for example, if I wanted to calculate the probability of a student in my class passing my class, I'd say that the probability of you passing my class should be around 95%. And I know some of you guys are like, you could just measure that from your previous data. I'm just going, no, I have a good feeling about this. All right, you guys, my 5th period, right? You're better than my 2nd period. And I think probability speaking, like you passing my class, I'd say it's about 95%. Yeah. Don't prove me wrong. I feel like I'm good on that one. I feel like that number is spot on, right? Maybe I should say higher, 99%. You know what? None of you guys are going to fail. All of you guys are going to pass my class, right? 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 I still haven't graded your test, by the way. Oh, that's what I forgot to do. I got to do that this weekend. Your finals are next week, which we'll talk about. How much time we got? We got about 18 minutes. I always forget we have homework. What, you don't believe it, Dema? I think you will pass. When will you actually grade them? Hopefully by the end of this weekend. If not, they have to be graded by December something. Not next Friday, but like, is it December something? I just had a meeting on this yesterday. Yeah. Anyways, Dema and Lizzie, if you forget about the homework, you can still do them. I still accept them, right? You have until next week Friday to turn them in. So if you haven't done any, if you're missing any homework, and they do go in as zeros, by the way, if you are missing them, you can go back and do them. Even if they're put in as a 0, just go do them and get them done. I will give you the credit still. I'm pretty lenient on homework. All right, let's take a look here. Classify the statement as an example of classical, empirical, or subjective, right? So remember, classical is the one that you do mathematically based off of what you can count. Empirical is what you do based off of what you observed out of how many times you've done it. Subjective is based off of intuition and an educated guess. So let's take a look at this one right here. The probability that you will get the flu this year is 0.1. The probability that you will get the flu this year is 0.1. Hope you guys can see that this one right here, this is definitely subjective. Definitely subjective, right? Probability that you will get the flu this year is 0.1. They don't really have anything that you can record to say that. They're not going out there and saying, oh, here's a population of 10 million people and 0.1 of them got the flu. They're not actually doing that, right? They don't know if everybody got the flu or not, or if they did get the flu, they don't record that down. If they never went to like the doctors to have that recorded, they would just rest and feel better, and then they would never know. So how'd they get this probability? It's basically subjective. It's based off of an educated guess, right? It's an estimate. Number 2, the probability that a voter chosen at random will be younger than 35 years old is 0.3. Now, this one could be subjective, right? Because they don't tell us that they did any observations, but you could observe this, right? You could actually ask how old a voter is and then divide that by how many people you've asked. So I could actually go up to 100 different people who are going to vote and ask them their age and record, is 30 of them less than the age of 35? And if so, then it comes out to 0.3. This one right here is done empirically. You can do this empirically. You could actually go out there and record how many people are under the age of 35 and then calculate the probability based off of what you've recorded. And that's what empirical probability is. That's all empirical probability is. It's just you're recording based off of what you observe. Number 3, the probability of winning a 1,000-ticket raffle with just 1 ticket. So that 1 ticket that you have is the winner out of a total of 1,000 total tickets. That's mathematically calculated, isn't it? Because it's just 1 ticket that's the winner out of a total of 1,000 tickets. This is classical. This is classical. Does that make sense? Hopefully. Is that okay? Is that all right? Does that kind of make sense on what's going on there? hopefully. Those are the difference between the three probabilities that you need to know. Classical is the first one we learned, right? It was basically you counting. Flipping a coin is 1 out of 2, right? Rolling a die is 1 out of 6. Empirical is basically off of what you can record based off of what you observe. And number 3 is subjective, based off of the fact that you can only do it based off of intuition and an educated guess. So I'd say subjective is the easiest one to identify. And Michael's asking for the difference between, I'm thinking you're asking for the difference between empirical and classical, right? Empirical and classical is probably the most hard to differentiate between the two. Because, like I said, classical is just basically what you can count from what is mathematically equal to each other. So the chances of you winning this raffle, right? If you only have 1 ticket out of a pool of 1,000 tickets, the chances of you winning is 1 out of 1,000. I don't do anything else. I just look to see what numbers are there. Empirical, on the other hand, you actually have to kind of record to see what the results are, right? So the chance of me choosing a voter who's younger than 35, I don't actually have like a paper value for people who are under 35. Instead, what I have to do is go and ask people how old they are and then record how many of them are under 35 and then also record how many people I ask. If I have to do that, right, to get that statistic, that's what empirical is. Empirical is just based off of that. Does that make a little bit more sense, Michael, about the difference between empirical and classical? I'd say that's the most difficult one to tell the difference between the two. But once you get the hang of it, it makes a little bit more sense, I hope. Yeah, like, for example, if I wanted to calculate what's the problem, just to keep it simple, right? Let's just say there's only 2 genders between male and female. And I wanted to see what's the probability of a student being male versus the probability of a student being female, right? Classically speaking, you'd say it's 1 out of 2. Empirically, you would go into like a classroom, like let's say my classroom, if I had students in here, and I would count how many males there are and how many females there are. And then if I wanted to see what's the probability of a student being male in Mr. Knockby's class, for example, you'd have to do that empirically, and you'd count, oh, there's 18 boys in here out of a class of 37, you know, and then you calculate the probability that way, and that would be considered empirical. Yeah. So that's the difference between subjective, empirical, and classical. Okay. All right. I got about 12 minutes. I'm going to go ahead and skip this. I'll leave this one up to you guys to fill out. Based on previous counts, the probability of salmon successfully passing through a dam on the Columbia River is 0.85. Is this statement an example of classical probability, empirical probability, or subjective probability? I'll let you guys decide which one of that one is going to be. And then number 2, classify this statement as classical, empirical, or subjective. The probability that you will be married by age 30 is 50%. Well, that makes me a little bit sad. I'm the other 50% that is not married by the age of 30. Or makes me happy. I don't actually know. Should I be happy or should I be sad that I'm not married by the age of 30? Calvin's saying sad. Both. There's a plus sign. Put a ring on it. Put a ring on what? All right. Let's wrap this up. So this is the idea here. If you're ever calculating probability, it needs to be between the range of 0 and 1. You can have it equal to 0. You can have it equal to 1. You can never have it be negative, and you can never have it be bigger than 1. Probability of 1 means that you're looking at the probability of 100%. And by definition, 100% is the most you can go. Just living your life more. Yeah, pretty much. So yeah, just keep that in mind. 1 is the highest, 0 is the lowest. And if you have ever calculated something where the probability comes out to exactly 0, that means that that event is impossible to occur. And if it comes out as a 1, it is guaranteed to occur. If it comes out as a 1 point something, you've done something wrong. Your calculation should never be more than 1. It could equal to 1. It could equal to 0, but it can never equal to anything bigger than 1. If you did your probability of E or whatever, and it came out to be 1.01, you've done something horribly wrong, right? Did I show you guys the Simpsons clip, by the way, of that? Have I showed you that clip? I think I have a couple minutes. I can show you this clip. Real quick. Unnecessary, but totally necessary. Wasted a little bit of time, but I love The Simpsons so much and their math-related stuff. I got to share this with you. Here we go. Share this. I'm going to mute myself. listen to this explanation of their explanation of something that's over 100%.
You are all very good players.
We are all very good players.
You will beat Shelbyville.
We will beat Shelbyville.
You will give 110%.
That's impossible. No one can give more than 100%. By definition, that is the most anyone can give.
So one of my like spot on lines I remember hearing as a kid. By the way, that came on in like 1993 or 94 or something like that. Very long time ago, before you were born. And I was a kid and I did not understand that joke. Like when I just saw it, I was like, they're being hypnotized. But when you break it down when I got older, I was like, oh, probability speaking, you know, they're telling the truth. That you actually can't go anything higher than 100%. And that's the case here, at least when you're talking about probability. Okay? All right. Let's take a look at this last example. I'm going to run out of time. Yeah, it'll be okay. Let's take about this last example right here. The complement of an event is the set of all outcomes in the sample space that are not included in the event, denoted as E prime. So what I want you to see here, it's supposed to be Mr. Rodriguez. No, he's not going to be showing you that. It's going to be Mr. Knockme who's going to show you this example. Mr. Knockme, right? So, for example, if I was telling you that event E, right, is to roll a 3 on a 6-sided die, right? So event E is saying that you want to roll a 3 on a 6-sided die. Do you know what E prime is going to be then? E prime is considered the complement, right? Meaning it's everything that is not included in event E. So if event E is rolling a 3, E prime, or the complement of E, would then be rolling everything else besides the 3. It would be including 1, 2, 4, 5, and 6. That's all the complement means, by the way. So if you're calculating the probability of one thing happening, the complement would be everything else that's not included in that event. So let's say I have another example here. Let's say I have event A, right, is to roll an even number, right, on a 6-sided die, right? So the sample space for this, right, for rolling an even number would be 2, 4, and 6, right? What's the complement of that, guys? Can you guys figure that out? What's the complement of event A? Anyone have any ideas? What's the complement of rolling an even number? What's the opposite, pretty much, of rolling an even number? What would you say? What do you guys think? What do you guys think? Complement of rolling an even number. Hope you guys can see it. Hope you guys can figure it out. I don't know. Remember, complement means it's the opposites, right? And Lizzie, that's it. It's the odd numbers. Don't say you don't know. You got it. You got it. If event A is rolling an even number, A with the little mark right there, A prime, means that it's everything that is not included in A. And what's not included in A? 1, 3, and 5. You see that? Flipping a coin and getting heads and tails, those are considered complements of each other. Probably of you flipping a coin and or the event of you getting heads, right? That's one event. Its complement is then getting tails. Does that make sense? They're basically, if you kind of count one for one event, its complement is everything else that doesn't get counted in that event. All right. So that's the idea behind there. So if you're going to roll an even, then the complement of even is odds. If you're just going to roll a number, its complement is every other number that's available, right? And it can go on and so forth. Yeah. So real quick here, right? You survey 1,000 employees and record the age of each. Find the probability of randomly choosing an employee who is not between 25 and 34. So you would not take the 366. You would take everyone else. I would take these numbers here plus that number there. So I wouldn't have to do all this extra math. I can just see that it's going to be those numbers right here. Boop, boop, and boop out of 1,000. Wait, that's it? Yeah. Is that all it's asked for? Yeah, so you got to know how to get that number, though. And then you could do the probability just like you would for the previous stuff. So for this particular problem right here, right, I would take those numbers right there. And I say, what's the complement of people who are between 25 and 35? Why, I would say that that complement would be equal to the total number of people in there, which is 1,000, minus 366, which comes out to be 634. So if I'm looking to calculate the probability of people who are not between the age of 25 and 34, where A is people who are between the age of 25 and 34, is going to be equal to 634 out of 1,000. Now, how do I get that 634? If you add those numbers in blue, you'll also get 634. But I did a cheater way by subtracting the number that I care about by the total number that I have there. So that would be it. This as a decimal would be 0.634, and then I'd be done as my answer. And we'll talk more about what the connection is for all that stuff. And dang it, I went way over time today. I think we spent way too much time talking about stuff. I feel like it's you guys to blame that get me sidetracked and talking about random stuff and we don't get to finish, even though it's probably my fault. But yeah, anyways, $550 headphones. No, see, this is what I'm talking about, Calvin. No distraction. Let me wrap this up. Let me finish this up here. Now I want to click on this link, but I'll click on it afterwards. I'm going to end this up so I can wrap up this recording. So we're pretty much done, right? This is the you try, and then there's extra problems, and there's homework right there. But I think we're pretty much done. But I did want to have a couple minutes here to talk to you guys about your final project, okay? So what I wanted to say is I think for your final, we're not going to be able to take a test on Unit 3, but you will have a cumulative final. And what I'm thinking for doing for your cumulative final is making it part like easy multiple choice questions that are going to be open notes, right? That you guys can look at to see how to answer them. And the notes that I'm going to ask you guys to use is your final project, right? Could you imagine if I were to give you a final and I told you guys, you can make a scrapbook of everything that you've learned from Unit 1 to now, and whatever you make, you get to use on the test. That's what the final project is going to be. The final project, right, is going to be you outlining everything you've learned from Unit 1 to now. So how do I want you to outline it? I want you to outline it however you want. And how you do it is going to tell me how many points to give you. There is no cap to how many points you can earn on the final project. So if you go over the required amounts, I will give it to you as extra credit. And there's no cap as to how much extra credit you can earn. Yes. So what does that mean? So if you go through here and you're starting your problems here and you start giving me definitions about, let's say from Unit 1, what does it mean for data, statistics, population, and sample, and you just copy and pasted this, I'll give you a point. If you copy and paste it and then you reword it into your own words that makes it understandable for you or someone else who doesn't like to read these long terms, I'll give you another point, right? And there's no cap on those points. And if you want to do a problem that explains it using either a video program or Google Slides where you can record your voice into the comments, the better, the more you do, the more points you can earn. And like I said, I don't want you to hold yourself back with any limitations on that, right? So anyways, well, again, I'll talk more about what I'm going to be expecting from you guys on this on Thursday because it is 12 o'clock now and I want to respect your time. And just keep that in mind right now. So I'll show you guys how to organize that stuff on Thursday, and then we'll talk about that and your final for next week on Thursday. All right, guys. It's 12 o'clock. I'm going to stop it there. So if you have some questions, you can ask me right now, but I'm going to end the recording and I'm going to say, just have a good rest of your day, and I'll see you guys on Thursday. All right, guys. That's it.